Okay, so let's start. So in the last couple of classes, we were looking at cones and convex cones. In particular, we defined what conic combinations are and what the conic hull of a given set is. So for any given subset of Rn, or in fact any vector space, you can compute the conic hull of that particular set. And we saw a few examples. So the most common examples are the ice cream cone, or in general any norm cone, and the positive or the non-negative orthant, that is a set of all vectors for which all the components are greater than or equal to 0. In R2, that would correspond to the positive quadrant, the first quadrant. Also, more importantly, one that will keep coming up is the cone of positive semi-definite matrices. So the set of all positive semi-definite matrices forms a cone. This is in the vector space of all symmetric matrices. Okay, and we saw an example of where conic programs come up. So we saw what second order conic programs are, and we saw that robust linear programming can be posed as a second order conic program. Right. So we'll continue our discussion of cones in this particular class. In fact, we'll restrict ourselves to a specific class of cones, and we'll see that they have some pretty nice properties. So I'll define a proper cone as any cone which satisfies these four properties. Right. So firstly, it's a cone that is convex. So given any 2 points, x1 and x2, that belong to the cone, every convex combination should also be in the cone. Right. Another way to say this is that the proper cone is closed under all possible conic combinations. Right. The second property that we'll require is that the cone be closed. Right. So can you give me an example of a cone which is not closed? No, it's a closed set, right? So for example, you should be, if it is not closed, then you can find a sequence of points that converges to a point outside the set.
Half space not including the boundary.
A half space not including the boundary. Which half space?
A transpose is greater than.
Okay, so A transpose X greater than 0. But remember, it should include the origin, right? Because 0 times X should lie in the cone. Correct? So can you make a small modification to your answer to ensure that it is a cone? Correct. So basically you take a cone, in fact any example that you can think of, remove some of the boundaries. Right? For example, you could think of the set of all x1 comma x2 in R2 such that x1 is greater than 0, x2 is greater than 0, or x1 and x2 are both equal to 0. Right? So geometrically this would correspond to the non-negative, the first quadrant, but without the axis. Right, so it's the entire first quadrant not excluding these two axes, but it does include the origin. We have to make sure that the origin lies in the set, otherwise it will not be a cone, right? So for a cone to be proper, it has to be closed, right? So this would be an example of a cone that is not proper. The third property that we'll require is that the cone be solid, or in other words, the cone K has a non-empty interior. So there exists some epsilon greater than 0 and some x lying in the cone such that you can draw a ball around x and still lie completely inside the cone. Okay. And the fourth property that we will require is that the cone be pointed. It says that if x belongs to K and it's a non-zero vector, then minus x cannot belong to K.
So
how is the solid property different from? So in this, there should be some x, right? But for a set to be open, we want to make sure that for every x in K, you should be able to draw a ball around. This is not so restrictive. So in particular, if a cone has non-empty interior, what can you say about its affine dimension? If you're looking at a cone in Rn, let us say, it should be n, correct? So it conforms to our geometric notion of solid objects.
then closed property implies
No, not necessarily, right? So let's see an example where each of these are violated. Okay. So first, can you give me an example of a cone which is not convex? Two rays, right? Okay, fine. So let's look at examples. So how would you mathematically describe the union of two rays? Or how would you describe a ray? Okay, take a point and then? Right. So it's basically you take a vector v. So a set of all x that can be written as alpha times v for some alpha greater than or equal to 0. This would be a ray, and the union of two rays alpha times, let's say, u so that would be suppose I have some vector, let me call this u, and this is some vector v, then the ray passing through u is the set of all alpha times u for alpha greater than or equal to 0. The ray passing through v is the set of all alpha times v for some alpha greater than or equal to 0, and the union of these two gives me the union of these two rays, and this is a cone, right? But this is non-convex because if I take any point on this ray and any other point on this ray, the straight line joining these two does not belong to the cone, right? So this is an example of a non-convex cone. Is this cone solid? It is not, right? It's basically it's essentially a one-dimensional object. If I take any point on either this ray or this ray, and I draw any ball around it of any positive radius, then that obviously does not lie within the cone. It extends outside the cone. Right? So this is an example of a cone that is not convex, also not solid. But is it a closed cone? So take any convergent sequence of points lying on one of these two rays. Can it converge to something outside this set? Yeah. You can't, right? So what would a sequence of points from this set K be? So let me call K to be the union of these two, right? So any point in K is either some alpha times V or maybe some beta times U, right? So if you had to construct a sequence, what would it look like? So suppose that I take a sequence consisting purely of points on this particular ray. All right, so there'll be alpha 1V, alpha 2V, alpha 3V, and so on, where these alpha i's should eventually converge. If the sequence converges, then the alpha i's should also converge. All right. In this case, can it converge to a point outside this ray? Because you're taking a sequence of alpha i's, and each alpha I is greater than or equal to 0. If it converges, what should it converge to? Some non-negative number, right? Because I'm taking a sequence of non-negative numbers, it should converge to some non-negative number if it converges at all, right? But that would be some alpha star, right? So the point that it eventually converges to is some alpha star times V, which is still in this particular set. The same holds true if I take any sequence of points lying purely in this particular ray. Now, what else can I do? I can also take sequences of points both from alpha times U and beta times V, right? Or maybe I can take a point from here, next I take a point from here, and so on. Now, if this sequence has to converge, maybe I take an alternating sequence. I alternately take points from this ray and this ray. If this sequence converges, where can it possibly converge to? Either it has to converge to one of them, right? But if it is continuously alternating, then at what point can it possibly converge to? Yeah? So consider a sequence of the form, say x k equal to some alpha k times u for k odd, and it's equal to some beta k times v for k even. Okay, so essentially I take a point here and then a point here and then a point here and then a point here and so on. Now if this sequence has to converge, what possible point can it converge to?
Yes, we can start. Even
Can it converge to any point in between? Remember, it has to converge, which means that the points should come close together, right? The only point that this can converge to is the origin, right? If it is any other point, then obviously if it converges to any other point, it cannot converge to any other point, because the very next point should lie for any point for sufficiently large n, xn is going to be in this line for n odd and this line in n for n even. And if these points must come close together eventually, then the only point they can converge to is the origin. This is again, I'm explaining this in an intuitive manner, not giving a formal proof of this, but nevertheless, it is impossible to construct a sequence of points, a convergent sequence of points, that does not converge to a point on this line or this particular line. So this is in fact a closed set. Is this pointed? So if I pick a non-zero vector in K, let's call it X, then does minus X belong to K? No, right? For any non-zero X that lies in K, minus X does not belong to K. So this is in fact pointed. So let's look at our example of the non-negative octet. Right? So this is the set of all x in Rn such that xi is greater than or equal to 0 for all I. In R2, this just corresponds to the first quadrant. Is this a cone? Yes. Okay, because you take any non-negative, any vector with all entries being non-negative, if you multiply it with a non-negative number, the entries will still remain non-negative. So it still lies in K. Right? So obviously this is a cone. Is it convex? It is convex. In fact, it's closed under all possible conic combinations. You take any x1 and x2 in K. So all the entries of x1 are greater than or equal to 0. All the entries of x2 are greater than or equal to 0. So if I take any theta 1 x1 plus theta 2 x2 for theta 1 greater than or equal to 0 and theta 2 greater than or equal to 0, then obviously all the entries of this particular linear combination should also be greater than or equal to 0. Right? So this will also belong to K. So this is in fact convex. Again, the picture to keep in mind is the first quadrant, right? Is this closed? It is in fact closed because you take any sequence of points, any convergent sequence of points where all the entries are greater than or equal to 0, this will eventually converge to a point where all the entries are greater than or equal to 0. It is not possible to have this converge to a point where even one of the entries is negative. So this is closed. And is it pointed? You take any x, any vector x in K. So consider any x in K. Suppose that minus x is also in K. Okay. When can that possibly happen? When xi is equal to 0, right? When xi equal to 0 for all I. Right? It's not possible to have a non-zero vector for which even one entry is negative. Right? So it is in fact pointed. So the non-negative orthant is in fact a proper cone. Yes, it's also solid. I think I missed that. And why is it solid? Right? So you can take some point, take any vector for which all the entries are strictly greater than 0. Right? Just take an example. Let's say 1, 1, 1, 1, 1, the all ones vector. Now, if I consider any ball of sufficiently small radius, I can very easily construct a ball of small enough radius. Let's say radius equal to half. Right? Then I can draw a ball of radius equal to half and never leave the non-negative orthant. Right? So, sort of geometrically, if I consider R2, I'm considering 1, 1. If I draw a ball of radius half, then it would look something like this. Right? And this is completely contained inside the cone. Right? The cone includes the entire first quadrant. Okay? So as long as I can draw a ball, a solid ball inside the particular cone, no matter where it may be, it is a solid cone. So this is an example of a cone that is convex, closed, solid and pointed, and therefore it is a proper cone. Right? Any questions? Okay, let's consider another cone. Take any subspace. Is this a cone? Yes. So it's closed under all possible linear combinations. So it's in fact closed under conic combinations. It's a convex cone. Right. What is the next property we need to verify? Is it closed? It is closed. Is it solid? Maybe. So if it's a subspace and it is solid, then so which subspace of Rn would be solid? Yeah. So remember, when I say a ball of radius r, I mean the n-dimensional ball of radius r, right? Of radius epsilon. See, I should be able to draw an n-dimensional ball of some radius epsilon. I should be able to fit in an n-dimensional ball inside this particular cone. Is that enough? So for example, let's think of R3. What would be a subspace of dimension 2? That would be a plane, right? Can I fit in a 3-dimensional ball inside a plane? You can't, right? So the origin is always included in the subspace, right? I'm sorry, I didn't. Can you repeat? Correct. I should be able to fit a solid sphere, and so for example in R3 I should be able to fit a 3-dimensional ball inside the cone. The center can be any point, right? The center of the ball can be any point inside the cone, but it should be a, so in R3 that would be a solid ball, in R2 that would be a circle, in R4 it would be a 4-dimensional ball, and so on, right? So if a subspace is solid, then what can you say about the dimension of that particular subspace? It has to be equal to n, right? So it should be Rn. So it's solid only if the dimension is equal to n. If the dimension is any less than n, then it is not a solid cone. Is it pointed? Is it possible to find some vector, some non-zero vector, for which both x and minus x belong to the cone? Yes, right? In fact, take any non-zero vector in the subspace, minus x has to belong to the subspace by definition of, because the additive inverse must exist, right? So it cannot be pointed, unless of course it is the trivial subspace containing only the zero vector, right? So it is never pointed. It's a 0-dimensional subspace. So in other words, no subspace of Rn can be a proper cone. Okay. So in fact, all of this has a geometric interpretation, right? What does it mean for something to be, so if you had to think of a cone, if you had to visualize a cone in R3, right? Let's take the ice cream cone. Okay, just even without proving, just to build some intuition, is this a convex cone? Yes, right? Is it closed? Yes, that is also closed. Is it solid? Intuitively, it is a solid, right? In R3, the ice cream cone is in fact solid. You can draw a ball around it. You can fit a ball inside the ice cream cone. Is it pointed? I mean, geometrically. So you see that it's essentially pointed at the origin, right? And even mathematically, if you think about it, you take any vector on the ice cream cone, what would be the negative of that particular point? That would just be the negative, that would sort of, it's a reflection around the origin, and that point is not included in the cone, right? So in fact, this definition of the mathematical definition of pointed, in fact, conforms to our intuitive notion of pointedness. Okay, so in R2, suppose I had to draw a cone, what would it look like? Yeah. Right. So basically, I just take two rays and the entire region in between those two rays, right? The region enclosed by these two rays. So when would this still remain a proper cone? So no matter how I chose these two rays, as long as they are two distinct rays and I take the entire region in between them, it will always be convex. Right? It's always guaranteed to be convex. Is it going to be closed? Yes, it will also be closed. Will it be solid? Yes, because within this I can draw a ball of sufficiently small radius. No matter how close the two rays are, I can always draw a ball of sufficiently small radius inside the cone. When will this be pointed? Yeah, so when the angle between them is less than 180 degrees, right? As long as the angle between them is strictly less than 180 degrees, it will remain pointed. That's both intuitive as well as by definition, right? As long as this angle between these two rays, I call this theta, as long as theta is less than 180 degrees, it's pointed. Because as soon as the angle is at least 180 degrees, I can find a vector for which minus a non-zero vector x for which minus x is also inside the cone. Right? For example, if theta is 180 degrees, then it means that I can take some point on this particular ray, then minus x will belong to the cone. If theta is greater than 180 degrees, it becomes even more easy. Right? It's only when theta is less than 180 degrees that mathematically it is pointed. Also geometrically it is pointed, because there is a, at this point, I mean at the origin, it is sort of so sharp. Any questions so far? Okay, so this was all in Rn. Let's look at the space of symmetric matrices. Right? What about the set of positive semi-definite matrices? We've seen earlier that this forms a convex cone, right? Because you take any conic combination of positive semi-definite matrices, that the resultant is also a positive semi-definite matrix, right? So this is convex cone. Is it closed? It is closed. Is it solid? So in this case, what does it mean to be solid in the space of symmetric matrices? Because we're all used to thinking of balls and objects in Rn, right? So when we're looking at the space of symmetric matrices, we can't rely just on pure intuition anymore. We have to think about mathematical definitions, right? So what is a ball? So again, what is the norm on the set of symmetric matrices? Yeah, which is correct. So that's sort of a distance, right? So what is, or more precisely, what is the inner product between two vectors or two matrices? Correct. So it's a trace of A transpose B or AB transpose. So the inner product between any two matrices A and B was equal to the trace of A transpose B, or the norm of a matrix A is basically the square root of the trace of A transpose A, right? And this essentially just corresponds to taking the sum of squares of entries of A. Right? So let me perhaps put this in a separate page. But over the set of let's say symmetric matrices, right? What does the trace correspond to, or what does the inner product correspond to? Let's say I have a matrix of the form A, B, C, C, right? Remember, in a symmetric matrix, in a 2 by 2 symmetric matrix, there are just 3 degrees of freedom, right? We can think of this also equivalently as a vector of length 3, A, B, and C, correct? So what would the norm of this be equal to? The square root of, it's A square plus B square plus 2 times C square. In general, if I have a matrix A, what would the norm be equal to? Suppose I have a symmetric matrix A. Correct. So it's the sum of squares of all the diagonal entries plus the 2 times the sum of squares of all the entries above the diagonal. So I can write this as summation over all I, AII square plus summation over all I, summation j equal to, say, I plus 1 to n, 2 times Aij square. You can verify that this is the case for any general symmetric matrix, 3 by 3, 4 by 4, and so on. Okay, so that's the norm, but what does a ball correspond to? So in the set of symmetric matrices, you take any matrix A, a ball of radius epsilon around A would basically the set of all matrices X all symmetric matrices X such that the norm of X minus A is less than or equal to epsilon. So we're just looking at symmetric matrices. So the goal is to, so the set of positive semi-definite matrices is not a subspace, right? It's not a vector space. It's only a cone, right? So this lies in the space of symmetric matrices. So throughout will be, when we define a ball, it will be with respect to the underlying vector space. And the underlying vector space here is the set of symmetric matrices. Okay, again, think about, let's say, R2, right? So this was a cone, but where did the underlying ball lie in R2? It should lie inside the cone, I know. But in general, a ball is defined over R2, right? It's a circle in R2. In R3, it's a solid ball, right? Similarly, here we want to ensure that there is some point inside the cone for which this ball lies inside the cone. All right. So now going back to the set of all positive semi-definite matrices, we want to find out whether this is a solid cone or not. So if in order to prove whether this is solid or not, what would we have to show? We should be able to show that given there should be some positive semi-definite matrix. So for this to be solid, there should exist some positive semi-definite matrix A such that some positive semi-definite A and some epsilon strictly greater than 0 such that the norm of x minus A is less than or equal to epsilon implies x is also positive semi-definite. Right, I should be able to find a ball. So the set of all x for which the norm of x minus A is less than or equal to epsilon is the ball of radius epsilon around A. So I should be able to find some matrix A and some epsilon greater than or equal to 0 such that as long as this happens, x is also positive semi-definite. Right. So let us maybe take some particular matrix. Let me take the identity matrix. Is this a positive semi-definite matrix? It is, right? So in order to prove this, I want to show that as long as this happens, right, I should be able to have, so for all x such that norm of x minus I is less than or equal to epsilon, x is also positive semi-definite. Let's take a 2 by 2 case, right? So effectively, what do I want to show? As long as A, let me say A, B, C, C minus I, what is this equal to? It's A minus 1, C, C, B minus 1. My goal is to show that for any such matrix, as long as the norm of this, or in other words, A minus 1 the whole square plus B minus 1 the whole square plus 2C square, as long as this is less than or equal to some epsilon, let's say 0.1, this matrix is positive semi-definite. All right. So is this true in this particular case? So how do you verify whether this is positive semi-definite or not? Okay, x transpose Ax is greater than or equal to 0. But would you verify, how do you actually verify that. Okay, and eigenvalues. So what can you say about the eigenvalues of a 2 by 2 matrix, a 2 by 2 symmetric matrix? Yeah, I know if it is positive semi-definite, but I'm just giving you a matrix of this particular form and having and satisfying this particular condition. How do you know, or how do you verify that this matrix is positive semi-definite? Or let me pose it a little differently. Is it possible to come up with a general condition on 2 by 2 symmetric matrices such that this is positive semi-definite?
Take the characteristic equation of the matrix.
Okay,
The roots are greater than.
correct. Both the roots should be greater than or equal to 0.
The condition.
It should have.
You can derive some conditional coefficients of
Okay,
such that the roots are greater.
okay. So let's just try to work that out. What would be the characteristic equation for this? Okay, so again, so lambda I minus a would be lambda minus a minus c lambda minus b. So the characteristic determinant of lambda I minus a would be lambda minus a times lambda minus b minus c square, which is what? It's lambda square minus lambda into a plus b plus ab minus c square. So if you're given such a quadratic, what are the conditions under which the roots are always greater than or equal to 0? Yeah? Okay, discriminant should be less than or equal to 0. So what is that equal to? A is PSD if and only if. Yeah, can you repeat? Yeah. A square plus b square plus 4c square minus 2ab is less than or equal to 0, right? So b squared, so a plus b the whole square. Okay, so can you simplify this a little bit? A minus b the whole square should be less than or equal, or a minus b the whole square plus 4c square which is not possible. Okay, okay, is that the only set of positive semi-definite matrices we can have? Okay, but is that the only positive semi-definite matrix? Yeah, correct. But can you construct a positive semi-definite matrix which does not satisfy this? So what if I take 1 0 0 2? Is that positive semi-definite? It's not positive semi-definite. Okay, so did we go wrong somewhere here? Can we check the conditions again? Which one? Correct. Correct.
We can apply that if the whole quadratic equation is
Correct.
we are not sure that the quadratic
You're not sure. So what should you be really checking? Yeah? Correct. So what we want are the eigenvalues, right? We want to ensure that the eigenvalues are strictly non-negative. Yeah? A plus B is positive, and how do you get that? So, okay. Correct. But is that enough? And why? Okay, but it's assuming that they're both real, right? But what if they're complex? Correct. So it suffices to just check whether for you know that for a symmetric matrix the eigenvalues are always always real. So it just suffices to check the trace and the determinant of the matrix. All right. So all you have to verify is that the sum of the eigenvalues is greater than or equal to 0, and the product of the eigenvalues is greater than or equal to 0. So what conditions do you get? So you want A plus B to be greater than or equal to 0, and AB minus C square is greater than or equal to 0, or AB is greater than or equal to C square. Okay. Now going back to this particular example, suppose that I have a matrix of this particular form. Does this equation guarantee that both of these conditions are also satisfied? Suppose I give you real numbers A, B, C such that this is satisfied. Does it mean that these conditions are also satisfied?
this is the distance metric, the equation indicates the distance metric. So we can write the equation of greater than or equal to 0.
Fine. So we know that this quantity is so in fact there are two things. One, this is less than or equal to 0.1, but this quantity is also greater than or equal to 0. Okay.
So you can form a quadratic
Okay.
and the quotient is greater than 0 and the equation is greater than 0, so we can apply the condition is less than.
Okay.
So then we can get the above.
Okay. Can you? Okay. But is there some easier way to check that this is in fact true? Okay. Roots of which equation? So there are three variables, right? A, B, and C. Yes.
We can check the eigenvalues of the matrix.
Okay, but how does that help? So I want to show that for every ABC satisfying this particular condition, it also satisfies these two conditions. Sorry? Okay. 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 True. But I want to show for all possible ABC. Okay. Correct. 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 So in other words, a minus 1 the whole square should be less than 0.1. B minus 1 the whole square should also be less than or equal to 0.1, and 2c square should also be less than or equal to 0.1. That has to be satisfied. Right?
Minimum value of A and B is greater than the maximum value of C.
Okay.
So that will be like A we are already positive to make that. So
Okay.
if we take any negative value, it will be more than 0.1. So A and B will be for sure positive numbers. So we can say A must be greater than 1.
Okay.
And A B maximum value is greater than C minimum value. So we can say multiplication of A B is greater than C.
Intuition is right, but okay, so I'll just leave it as an exercise to in fact show that that is true. So it should be much easier. This is in fact a much stronger condition than these two sets of conditions, right? Ultimately, it is just manipulation. There's nothing more to it. So show that, let me call this equation 1, implies that A is positive semi-definite. I could have chosen a slightly larger number instead of 0.1. It works only for two-dimensional matrices. True. So in fact, you can prove this for a general n by n symmetric matrix. Okay, I leave you to think about it a little bit to see how you could possibly. So you'll need something more, right? You'll need some sort of a general result. Effectively, what you have to show is that as long as the norm is sufficiently small. So in this case, I could choose a specific number 0.1. But in fact, what I'll need to show is that as long as, let's say, A is very, very close to I, it is definitely going to be positive semi-definite. Okay, it requires a little bit of thought, and you need to use some additional tools. Recall all the results that you've seen in linear algebra. Sorry? Nothing that fancy, just using things like spectral theorem and so on. Spectral decomposition should be enough, but I leave it, I mean, think about it for some time, right? If not, I'll give a complete proof of that in the next class. But I do want you to think about it a little, because it's useful to try to understand how the set of symmetric matrices behaves, right? And how the set of positive semi-definite matrices behave. In fact, what you can also show is that if you take the set of all positive semi-definite matrices, the interior essentially just becomes the set of all positive definite matrices. So in fact, in order to prove that A is the set of all positive semi-definite matrices is solid, I don't necessarily have to take the identity matrix. I can take any positive definite matrix and show that there exists a sufficiently small epsilon such that this happens, right? Such that the ball of radius epsilon around it is completely positive semi-definite.
So the matrices which satisfy solid property are opposite of
Correct. So every positive definite matrix, you can draw a ball around it. So it's an interior point.
solid.
Correct. So at any interior point is fine. And okay, so let me give some more hints. So basically, you take any positive definite matrix, you know that all the eigenvalues are greater than or equal to 0, right? Effectively, what you have to do is consider the smallest eigenvalue, right? If let's call that lambda min. Okay, so let's say you take something like a ball of radius lambda min by 10, or anything, in fact, something that's much smaller than lambda min, then you have to prove that any ball of radius less than lambda min by 10, in fact, anything less than lambda min is also sufficient. You draw a ball of this particular radius around it, that will still be positive semi-definite. Right? Just try to think about it a little bit. Which one? The set of all positive definite matrices, in fact, is an open set. The set of all positive semi-definite matrices is a closed set. It's closed. Okay, so in fact, you can prove that this is a solid cone. Is it pointed? So take any non-zero matrix, any non-zero positive semi-definite matrix. Will minus A be positive semi-definite? It cannot be positive semi-definite, because there would be at least one vector x such that x transpose Ax would be less than 0, strictly less than 0. Right? So this is in fact pointed. So the set of positive semi-definite matrices, this also forms. So this is a proper cone. Okay, so why are we focusing on proper cones? What do proper cones give us in comparison to just, let's say, normal convex cones? Why do I need the properties that should be closed and solid and also pointed? If I have a proper cone, I can define what is called a generalized inequality. Okay, so one example of a generalized inequality is component-wise inequality of vectors. Right. So let's say that x. So consider Rn. Let's say x1 and x2 are in Rn. X, y in Rn. I will say that x is less than or equal to y if every coordinate xi is less than or equal to yi. Okay, that's a natural notion of defining something like an inequality. Right? But one thing to note is that not every pair of points is comparable. So if I have 1 comma 2, this is definitely less than or equal to 2 comma 3. And it's greater than or equal to, let's say, minus 1 comma 1. But I can't compare 1 comma 2 with minus 1 comma 3. Right? Because 1 is greater than minus 1, but 2 is less than 3. Okay, and why would this sort of comparison make sense? So for example, suppose you have an optimization problem where you want to, let's say, optimize over multiple parameters. Okay, so suppose you have some kind of a problem where you're not just looking at one parameter. Let's suppose that you're doing some kind of portfolio optimization. Suppose you want to maximize your profit, but also minimize the uncertainty that is there, or the risk involved in getting that particular profit. Right? These are two different variables. They could be different functions. They could be two different objective functions, but you want to, in some sense, jointly optimize over both objective functions. Okay, so suppose you have some f1 of x and f2 of x, and loosely speaking, you want f1 and f2 both to be small. Okay, now this, you may be able to achieve some such, you may be able to simultaneously be able to minimize both, but more often than not, these two objectives are generally conflicting. Right? So it's possible that by reducing f1, you could in fact be increasing f2. Right? But in such scenarios, suppose I'm giving you two different x, right, x1 and x2. It's still may be possible to choose points which are, in which one point is, is definitely better than the other. Okay, so for example, suppose I plot f1 of x versus f2 of x. So this is f1 of x, this is f2 of x, and maybe for different x, so for every x I get 1 point in this plane. I get one value of f1 and one value of f2. Suppose my goal is to ensure that both f1 and f2 are small. Okay, and I consider two different points. Suppose this is one point and this is another point. So this corresponds to x1. So this is in fact f1, let's say, or f1 of x, comma f2 of x, and this is another y, let us say. So this is f1 of y and f2 of y. Now among these 2 points, suppose my goal was to ensure that both f1 and f2 are small, which one would you say is better than the other? Is x better or y better? Yeah. Suppose your goal was to ensure that both f1 and f2 are small. Y is better, right? Because for this particular, if I choose this particular y, in this case f1 of y is less than f1 of x, and f2 of y is less than f2 of x, right? So choosing y is obviously better than choosing x, but it's possible that 2 points cannot be compared. For example, suppose I take a point here, all right? Let me call this z. So this is f1 of z, f2 of z. In this case, f1 of z is less than f1 of y, but f2 of z is greater than f2 of y. So I can't really compare between these 2 points, but I can definitely compare between these 2 points. So how do I decide which points are better than other points? That's what I want to understand, and that's what generalized inequalities help us with, particularly when you have multivariable optimization or multi-objective optimization problems. That's one class of problems where generalized inequalities come from. But as we'll see later, when we deal with duality and so on, that these generalized inequalities help us in other ways. Okay, but one sort of canonical example to have in mind is when you have, let's say, 2 conflicting objectives and you want to minimize both these objectives somehow. So how do I describe, the question is how can I sort of describe this generalized inequality in terms of cones? Okay, so suppose that K is a proper cone, then I'll define the generalized inequality with respect to this proper cone. I'll denote this in this particular fashion. If y minus x belongs to the cone. So with respect to this proper cone, I have a generalized inequality, and with respect to this generalized inequality, I'll say that x is less than or equal to y if y minus x lies inside the cone. Okay, let's go back to that example that we have of component-wise inequality. Right? Suppose that x is less than or equal to y, or in other words, xi is less than or equal to yi for all I. Then what can I say about y minus x? I have yi minus xi is greater than or equal to 0 for all I. Right? That's all that I'm saying. So if I have 2 vectors and it so happens that every component of x is less than or equal to every component of y, then if I take y minus x, every component of this vector should be greater than or equal to 0. Correct? But what does this correspond to? If every entry is greater than or equal to 0, then it must mean that this vector y minus x should lie in the cone. So in R2, it has to lie in the first quadrant. Y minus x should lie in the first quadrant, or in general it should lie in the non-negative offset. Right? So in fact, let's pick any point in R2. All right, let's call this X. Considering this component-wise inequality, right? What is the set of all points which are greater than or equal to X? Suppose you had to plot the set of all Y for which Y is greater than or equal to X. So in other words, Y1 is greater than or equal to X1 and Y2 is greater than or equal to X2. Correct? So basically, I can draw these lines, and this entire region corresponds to, this is the set of all Y such that Y is greater than or equal to X, component wise. Correct? But essentially, what set does this correspond to? Yeah, which cone? Specifically, which cone is this? It's just the first quadrant, right? It's just a shifted version of the first quadrant, right? So in fact, I can do this not just with the first quadrant. I can define any proper cone. I can take any proper cone and define a similar generalized inequality, right? Let me just redraw that. So I have a point X. So this region is the set of all points Y such that Y is greater than or equal to X. What about the set of all points which are less than or equal to X? Yeah, so it's effectively a shifted version of the third quadrant, or in other words, the flipped version of the first quadrant. So this would be the set of all vectors which are less than or equal to X. So in other words, suppose I'm given two feasible points. I have, let's say I have an optimization problem where I have two different objective functions to minimize, if possible simultaneously, and I'm given two different points. One point is X. Then certainly if the point lies in this region, let's say if my Y lies in the green region or in the orange region, I can definitely compare. I definitely know whether one is better than the other. But if it does not lie in either of these regions, then it's not possible for me to compare those 2 points. I can't definitively say that one feasible point is better than the other feasible point in simultaneously minimizing both objectives. Right? Any questions? Okay, so let's stop here. This is conceptually quite different from what you've seen. There's a lot of new notions that came up. So just try to go through the notes once again. In particular, try to prove each of these statements for positive semi-definite matrices and cones and so on. And try to construct examples of cones wherein 3 of the properties are satisfied, but maybe 1 is not satisfied. Right? Try to think of examples of cones which are convex, closed, and solid but not pointed, non-convex but closed, solid, and pointed, convex cones which are closed and pointed but not solid, and so on, right? Because that will help you build intuition for these different kinds of cones. Okay. And also try to think about, try to prove this statement first for the 2 by 2 case, that if this property is satisfied, then A is positive semi-definite, and also that the set of all positive semi-definite matrices is solid. Okay, so let's continue in the next class.